So, to kick off your MTEL course, we're going to start on 0016. And this strand deals with, truly understanding our number system in all its sorts of representations and having a really good concept of place value. So really wrapping your head around, first we'll go over different types of numbers, just so that we can have the right language when we're talking about different subsets of the real numbers. We'll talk about decimal expansions, meaning fractions and their equivalent decimal representations. We'll talk about scientific notation and all the weird sorts of questions they'll ask you with that. We'll talk a little bit about estimation, and then we'll really look and see some properties of base 10 number systems and kind of how we can manipulate them and interact with them. So we're really going to be looking at numbers today and properties of numbers. And remember, in our informational class, we now feel more comfortable adding, subtracting, multiplying, and dividing, things like whole numbers and whatnot. But now we'll get into the nitty-gritty of different sorts of representations of numbers and how can we interact with them. Okay, so I recommend that when you're taking notes on these materials, I recommend that you write even more than what I write down. So feel free to pause the video, because I'm writing on the iPad isn't the most wonderful thing. So I'm going to say some things, and some of those things you should be writing down. I will write some things down, but try and get more than that down. So integers. Any number on a number line, like imagine, I think back to like 5th grade. Here is a number line. I think I had this taped to the top of my desk. So an integer is a number like 0, or 1, or 5, or 56. But also -1, -2, -3, etc. These are all examples of integers. Boom, boom, boom. So every single situation like this is an integer. So what I mean by that is 0 and any positive or negative whole number is an integer. So, for instance, in terms of your notes, you should write something like positive or negative whole numbers, including 0. And, you should be able to define that. Okay. So, a rational number. Now, if you look at the word rational closely, you can actually see the word ratio in there. And what ratio means is a fraction or a quotient of two numbers. So how do you make a rational number? Well, you take an integer, a, and you divide it by an integer, b, where b is not equal to 0. And a and b are integers. That's how you make a rational number. You make a ratio. Take any two integers, and just turn them into a fraction. So for instance, even with the things that I've listed up here, oh, by the way, you can't divide by 0, so b can't be 0. That would not make a rational number. That would either make positive or negative infinity, and that's for another day, for a rainy day. So now we have integers. We can make rational numbers by taking any integer and putting it over another one. So let's get a couple of examples there. So let's say I put 5 over 2. That is a rational number. By the way, it could also be represented as 2.5. And so we made a rational number. Pick another two integers. How about -1 divided by 3? Those are two integers written as a ratio or a quotient. So that is also a rational number. By the way, if you were to divide that out, that's -0.3333333, and so on and so forth. So -0.3 repeating. So that is also a rational number. -1/3 is a rational number. 5 halves. Pick any other integers you want. 7/9, 6/4, whatever you want. So just bear in mind that it is acceptable to have a repeating decimal representing a rational number. And we will actually talk about that later in the class. How do we do that? Last but not least are irrational numbers, meaning numbers that are not rational. So these are any numbers. Well, I'm going to go for an example first. So the most famous irrational number is pi. Why is pi irrational? Well, pi is 3.14159 ... Notice how the decimal expansion, the decimal representation, of pi never terminates, meaning it never ends, and it never repeats. There's no pattern in pi. Like someone, I think, can recite pi to 2 million digits. There's no pattern in there. Another rational number that's very famous is like the square root of 2. If you were to try and represent what times itself makes 2, you would have a decimal, a number that is a decimal, 1 point something, where it never terminates and it never repeats, just like pi. Actually, the square root of any prime number, that p there represents a prime number like 2, 3, 5, 7, 11, etc. They all will give you irrational numbers. So the definition of an irrational number is any number that doesn't terminate or repeat. And what we mean is its decimal representation does not terminate or repeat. So what's interesting is all three of these subsets of the real numbers make up the real numbers. So we'll kind of turn this into like a little bit more of a complete picture here now. Now, as a 5th grader, I have my number line that Mr. McCrudden gave me. So this number line, we could actually think of it as the real number line. In blue are the integers. Now, in red, let's make some rational numbers. Let's say, here is a half. Here is 13/7. Here is 3.5. Here is negative. Here is negative 1.8. Those are all rational numbers, and you could think of them, as fractions, like negative 7/3. That's negative 2 1/3. That is a rational number. And so there's actually lots more rational numbers in here. Like even if I just, looked at, here's 1/11, and here's, 1/3, and here's 1/5, etc., etc. There's lots and lots of rational numbers. And then our irrational numbers come in, so let's kind of go for black here. Things like pi, 3.14159, that interesting number that falls right there. The square root of 2, which is 1.4 without repetition or termination. That's like right here. So if you were to actually inlay all of these numbers, you would fill up this entire number line. All of these numbers together, they would fill up this entire number line, and they represent the real numbers. So an integer is a real number. A rational number is a real number. An irrational number is a real number. So real numbers encompass all of this stuff. So one important thing on your exam, we've gone over knowing different number types and their definitions and examples of them. One thing that you might want to do is sometimes in certain problems, changing the way the numbers look will help you gain insight into the problem at a deeper level, and we'll give you access to it and, get you to the right answer. So one thing that's important is if we look at fractions, they have decimal expansion. So like the fraction of 1 has a decimal expansion of 1. So we've got fractions and we've got decimal expansions. A fraction of a half has a decimal expansion of 0.5. Fraction of a third, we talked about that in the last slide, is 0.3 repeating. So you have to kind of recognize these things because they might throw a decimal at you and you'd have to think about, well, what is its fraction, or vice versa. A quarter, 0.25. A fifth is 0.2. Let's go for a couple more that we should have our eyes peeled for. Let's say we have a sixth. Let's actually figure out the decimal representation of a sixth. So what you'll do is you'll literally take 1 and divide it by 6. So lots of times on certain problems on the MTEL, sometimes you just got to, grind it out, divide it out, and see what you get. So how many times does 1 go into 6? It doesn't, so then we can look at 10. 6 goes into 10 once. 4 left over. Bring down to 0. 6 times 6 gets me close. It's like Price is Right rules. Gets me close to 40, but under. And as you can see, we keep bringing down zeros and getting lots and lots and lots of 6s. So that would be 0.16 repeating. That's the decimal representation of the fraction 1/6, and so on and so forth. So, I'm not going to give you a huge list that you have to memorize all of them, but have the confidence to divide out, the numerator divided by the numerator divided by the denominator, and see what the decimal representation of a fraction is. That might be all you need to make a problem that's weird, much more manageable. So I think it's important at this point to just remind you guys about scientific notation. Scientific notation is written as, you can take a number and you can represent it as a times 10 to the n. Now be careful. A must be between 1 and 10. It must be strictly less than 10. It can be the whole number 1. Okay? So let me kind of show you how to interact with this, and I'll actually give you guys a couple of exercises to work on here as well. So just to be clear though, if this is a non-example, like 72 times 10 to the 5th, that is not written in scientific notation. Why? Because that number A, that number in the front there, is not between 1 and 10. And again, it must be strictly less than 10. So that's not in scientific notation. Here's some examples of scientific notation. And what we're going to do is we're going to convert them from scientific notation to just regular old numbers. Okay, so let's say I had a 7.0 times 10 to the third. So this is an example of scientific notation because that A, that leading number, is between 1 and 10, and it could be 1, but it is certainly less than 10. So now if we want to convert this, what we're going to do is we're going to take this exponent. This exponent is positive. So, one feature of our number system that we have to be mindful of is if you have a positive exponent here, if you're multiplying something by 10 to the third, that's like multiplying it by 1,000, meaning that's 1 followed by 3 zeros. If you had 7 times 1,000, you would have the number 7,000. So this positive exponent makes your A value grow and, become larger. So it's important that what you do is you kind of just take your decimal place, and since this is positive, you're going to move 1, 2, 3 to the right. Now that looks kind of crappy, so let me show you that a little better. We had 7.0, we moved it 1, 2, 3 to the right, and then fill those in with zeros. That makes the number 7,000. Okay, so you're going to move to the right to make a larger number if your exponent is positive. Now, this is also interesting. Here's another example of something written in scientific notation, but it's going to kind of be different. So if we look here, we have 5.093 times 10 to the negative 2. So, oh, by the way, another feature, n will always be an integer, and now you guys are well versed in my math speak here. So this exponent is negative. So now what we have to do is think about, well, how is that going to move our decimal point? It's all about really locating that decimal point. And just to be clear, this a value is between 1 and 10, but less than 10. So we know we are in scientific notation. We're going to convert this to just the decimal representation. So we can take our decimal place, and now we're going to move it 1, 2 to the left. So we'll have 0.05093. So keep in mind there's that placeholder of a 0 here, and that's how we get our final answer here. I'll do one more example and then I'll leave a couple for you. So now instead let's go from just a regular old number, and let's turn it into scientific notation. So let's say I had 5,307,960. Well, to be clear, the decimal place is right there. Now what we'll do is we'll ask ourselves, how many decimal places do we have to move, and are we moving them right or left, to find our a value, to find our number that's going to be between 1 and 10 but less than 10. So we're at 5,307,960. That's too big. Still too big. Let's keep going, and let's keep a running count here. Okay, there we're at 53.07960. 53 is still bigger than 10, so we'll go one more. Boom, that's where our decimal place is going to go. That'll be 5.307960 times 10 to the, well, we went 1, 2, 3, 4, 5, 6. That'll be times 10 to the 6th. Now be careful, that's to the positive 6th, because this number is large. It's not a small decimal. So another thing that I should have mentioned, negative exponents do not make negative numbers. Like in this example, it makes a fraction or a decimal, a number less than 1, but it does not make it negative. So be very, very careful, because that would be a good wrong answer for a multiple choice. So just be wary of that. So again, this number 5 million is big. It's going to be a 10 to the positive 6 when we represent it in scientific notation. Our a value is between 1 and 10. So we know we have represented this in scientific notation. So we've shown in this how to go from scientific notation to decimal representation, and we've also seen vice versa, or the opposite. So I'm going to give you a couple, and I'm not even going to tell you what form they're in, and I want you to switch forms with them. So these are 2 for you. I'd like you to switch this, and these are the kinds of things we can talk about in class and make sure everyone's cool with them. Try and convert that, as well as, why don't we convert this? 2.09 times 10 to the negative 4th. So just convert those according to kind of the rules that we've gone over here, and we will get into weirder things for sure. All right, so what we're going to do is we're going to go over the property of rounding, and rounding is very important just in terms of estimation in life, but also in, in whatever sort of weird situation the MTEL might throw you into. They may have you round to a certain extent, to a certain digit, let's say, to a certain digit's place. So here's the general rule for rounding. All right, so the general rule here is, let's go through an example, and I'll kind of read you the rule through an example. So let's say we have something like 0.004867. So here's our example. And let's say the problem asks us to round to the nearest thousandths. Okay? So count with me. We've got tenths, that's 1 to the right of the decimal place, hundredths, 2 to the right, thousandths, 3 to the right. So this is the digit in question in the definition that I've provided above. So here's our digit in question. It's a 4. Now we're either going to leave it as 0.004 or we're going to kick it up to 0.005. It all depends on the digit after the digit in question. So let's really apply the rule. So if the digit 1 to the right, namely this 8, of the digit in question is 5 or more, we're going to increase the digit in question by 1. Otherwise, we're just going to leave it as is. Okay, so to round this to the nearest thousandths, we're going to take this digit 1 after the digit in question. It's 5 or greater, so we're going to kick this 4 up by 1, and we'll call this 0.005. I use squiggly equal signs. That means like approximately equal. And this is to the nearest thousandth. Okay, let's try another situation. Let's say we're asked to round 1.003951. And let's say this time we're asked to round to the not the nearest tenths, hundredths, thousandths, but let's say 10 thousandths. So we're going to focus. We're going to go to the nearest 10 thousandths here. So again, we're going to look 1 to the right. Is that 5 or bigger? Yes, it's 5, so it's 5 or bigger. So what we're going to do is we're going to kick up the digit in question by 1. So you got to think about it like this. That 9 is going to get kicked up, or let's think about it even like so. This 39 is going to actually get kicked up to a 40 because this 9 is going to go up to a 0, if you will. And so we're going to actually increase this by tenths, hundredths, thousandths. We're going to increase it by 1/10,000th, which is actually going to kick us up to squiggly equals, approximately equals 1.0040. So this is like the weird situation that I wanted to get in this video. We were looking to the nearest tenths, hundredths, thousandths, 10,000ths. We were looking at the 10,000ths, so we went to the 100,000ths. We said, okay, that's 5 or bigger, so now we're going to raise this by 1, which is actually going to raise this digit, the thousandths digit, by 1. And notice how when we write this out, we're still going to go to that 4th decimal place after the decimal, because that's how far they wanted us to go. So we won't call it 1.004, we will call it 1.0040. So this example is trying to illustrate sometimes when you have to kick one digit up by 1, if it's a 9, it's going to actually have an effect on making the digit before it 1 greater, and that 9 will go up to a 0. Okay, very good. All right, so here we're going to look at properties of our number system. We have a base 10 number system, and what we mean by that is there's different powers of 10 that really can be used to represent any number. And I'm assuming the reason for this is because we have 10 fingers and 10 toes. But so let's actually look at a number, and we'll kind of write it in its expanded form, and then we'll even look at all of the powers of 10 that make up that number. So let's try this guy right here. How about we have 456, 328. And let's say we're asked to write the expanded form of this number. Well, one thing that's interesting is we can kind of think of this number in 6 parts, because there's 6 different digits making up this number. So here's how I'm going to approach this. I'm going to think of this number as, first, if I just asked you, what is this? Well, there's a 4 in the hundred thousandths place. So that's 400,000. And then next you'd say, and then there's a 5 in the 10,000ths place, otherwise known as 50,000. And there's a 6 in the thousandths place. And there's a 3 in the hundreds place, a 2 in the tens place, and an 8 in the ones place. Now, this number, 456,328, is equal to the sum of all of these 6 numbers. I'm kind of breaking it down one digit at a time. So now let's kind of write it a little bit more differently, and then we'll actually get to our powers of 10. So 400,000, that means there's 4 hundred thousands. 50,000, that means there's a 5 in the 10,000ths place. Similarly, 6,000, that means there's a 6 in the thousands place, so there's 6 times 1,000 there. There is 3 hundreds. There are 2 tens, otherwise known as 20. And then there is 8 ones. I'm going to write it like this, and I'll kind of mess with it in a moment. Okay, so again, I have equal signs everywhere here. This number is equal to this mass, which can be represented as such. Okay, now here's the powers of 10. Well, again, we're really just kind of picking off these digits, and then we're kind of changing the way the rest of the components of the digits look. All right, so we have 4 times 10 to the what? So this is going to be an important feature of our number system. We have 1, 2, 3, 4, 5 zeros here. So that's 4 times 10 to the 5th. That's another way to say 4 times 100,000, or 400,000. Let's do our next, add to that. Our next digit, let's actually, we'll keep going this way. So now we have 5. So then that's going to be times, now how many zeros do we have here? 1, 2, 3, 4. That'll be 5 times 10 to the 4th. So 10 to the 4th is otherwise known as 10,000. 1 followed by 4 zeros. All right, let's keep it going. Then we have 6 times 10 to the 4th, because that 10,000 is 1 followed by 4 zeros. Keep it going. Then we have 6, in the same vein, count your zeros. We have 10 to the 3rd there, otherwise known as 1,000. Then we have 3 hundreds. 10 times 10 is 100, otherwise known as 10 squared. Plus, we have 2 tens. And that'll be 2 times 10 to the first, 2 tens. And then we have we have an 8 in the ones place. Now you might ask yourself, well, what power of 10 is 1? Well, if you kind of look at the pattern we've made, and on the bottom of the slide the colors have kind of gone a little awry, you can kind of see that since we have consecutive digits here, we had powers of 10. We have 10 to the 5th, 4th, 3rd, 2nd, 1st, go down by 1 again. That's right. 1 is 10 to the 0 power, so you can kind of follow this pattern. So here's an interesting way to expand the number 456,328. And notice the powers of 10 because we have a base 10 number system. So a little bit of practice here for you. I'd like you to expand $7,021,104. So try and expand that and write out the powers of 10 just like we did on the last slide. Also, let's say I give you this sort of number. So here's an example for you to try. Let's say I gave you 5 times 10 to the 6th plus 2 times 10 to the 3rd plus 1 times 10 plus 6 times 10 to the 0. And just to get interesting here, plus 2 times 10 to the negative 1. Could you write that number not in expanded form? So try and go the opposite way. And these are the kinds of things we can talk about in class and explore further, and then see what sorts of situations the MTEL will put us in. Good luck. I hope this video was informative. Have a good day. Bye.